Without further ado, I'll introduce Suzanne Foss. She's a product manager at ESRI in the analytics and data science space, and she's going to be talking to us about trends in spatial data science. Thanks, Suzanne.
Thank you very much. I'm really excited to be here. I know that sounds kind of rote, but I've never been to an ArcGIS user group before, and it's really exciting to me that everybody's here and learning from each other, and it just warms my heart. So thank you for having me. So yeah, my name is Suzanne Foss. I am the primary product manager for analytics and data science at ESRI. I've been at ESRI about 14 years, so I'm coming up on 15 years in January, and I'm really looking forward to my next increase in vacation. I'm just kidding. I think it's at 20 years. All right, so I do have an ambitious agenda today. We're going to go ahead and get started because I'm sure everybody will want to get to the social when we're all wrapped up. So we'll go ahead and get started with just kind of some definitions and some context. What do we mean by spatial data science, at least at ESRI? So spatial, or actually I should just say data science itself, is a pretty trendy term. You hear it a lot these days. Everybody wants to brand themselves as a data scientist. And depending on who you ask or what source you look it up in, you get different definitions these days. So in some cases, you'll hear that it refers to a life cycle of data collection, of data storage and maintenance, data processing and data mining, and that it involves automation. And at the end of it all, you have to communicate your results. But if you think about it, that sounds pretty much just like the general analytics workflow that probably many of us have been following for years. Others characterize data science as being highly quantitative, creating complex quantitative algorithms, performing predictive analysis, and building machine learning models that predict outcomes, and that often data scientists have to have scripting and programming skills to do what they do, and that they often have subject matter expertise in their areas of work. But again, it's not like those activities are entirely distinct from analytics either. So one useful way to look at all of this is that analytics and data science exist on a little bit of a continuum, and there's lots of overlap between them. But as the work of getting insight from data begins to become more involved in statistical inference, as data gets bigger, and as you begin to be more involving AI and machine learning techniques in your work, and it's kind of heading towards that end versus being a little bit more exploratory and sort of summarization types of analysis, then you're kind of in the data science end of the spectrum, if you will. But the reality is that these distinctions are pretty blurry, and it probably normally doesn't matter. What matters is that we're applying the right algorithms and that we're using the best tools to solve our problems. So with that, what is spatial data science? So someone said to me the other day, I don't know if this will resonate with any of you, but someone said to me, you know, the only people who call themselves spatial data scientists are the people who started out in GIS. And that may be true. But I would probably argue that, and I think many of you would as well, that GIS has for years encompassed a lot of these activities or skills that we just talked about. GIS is highly quantitative. We're often using statistics to find clusters or patterns. We're using scripting and automation to make workflows repeatable. And statistics are heavily relied upon. And of course, a lot of times we like, at least at ESRI, we like to pride ourselves on working with users that don't necessarily call themselves GIS practitioners. It's, no, I don't do GIS. I use GIS to make my work better. So again, a lot of GIS users are subject matter experts. So one way to look at spatial data science is that it's really the application of the geographic approach into analysis and data science work. So the geographic approach is something that's kind of always formed the foundation of geographic information systems. Broadly, it refers to the ability of geography to integrate and be an integrating element for considering a problem and for taking lots of different factors and looking at them together. So social factors like demographics, equity, education, economic factors like industrialization, development, and energy, and of course, environmental factors like weather and climate and terrain and ecosystems. And of course, none of these exist in a vacuum. And they all influence each other. And certainly a lot of us who work in the GIS space believe that geography has this really unique power to allow you to synthesize data from different places and form a more complete picture. Within ESRI, we think about spatial data science as kind of, we look at it and focus on it in terms of supporting all of the different phases of data science work. So spatial data science, we kind of, again, consider analytics and data science a continuum, so we kind of usually group them together. And it includes everything from data engineering, where you have to get your data ready for analysis. You might discover missing values in your data that you have to correct or exclude, to visualization and exploration, which is sometimes where analysis begins and ends, is just seeing data together and being able to understand where you need to focus your attention. In the middle here, I'm listing spatial analysis again, which may seem repetitive, but what we mean by this here are the actual algorithms and the methods that you might apply to solve a problem. So is it a network solver? Is it a vector overlay? Is it a raster function? And so forth. Modeling and scripting is all about making the workflow repeatable or making it self-service so that somebody else can actually run it. And then finally, sharing and collaboration is kind of where it all ends. And that's true for really any workflow, but it's so important with analytics. You know, if we want the work that we're doing to matter and the work that we're doing to influence decision-making, then it can be really, really important that our analysis and our results are shared in appealing and dynamic ways so that decision makers understand the process and then they can trust it. So within spatial data science, there's a lot of really exciting and innovative areas. Automation has always been part of GIS, as we've said, but new experiences like notebooks are making it even easier and broadening that pattern. Sensor and IoT data are increasingly available to different organizations, and so that makes it necessary in some cases to process data in real time. And then real-time data and also advances in 3D data are allowing a lot of organizations to put together digital twins and have these wonderful realistic models of their environments that sometimes also enable simulation. And a lot of these trends are related to each other as well. So as data comes in real time, it turns into big data, requires big data analytics, which we're going to get into. And because that is often driven by data that comes in real time, there's usually a time component. So then you need to have advanced spatiotemporal algorithms to work with your information, and so on and so forth. And we could probably talk a lot about any of these today, but I kind of picked 3 to focus in on, partly because these are really top of mind areas that we see a lot of our customers at ESRI pushing into, but also because they're key areas of research for us at ESRI. So we have fun things that we can show you. All right, so the first one we're going to focus on is big data analytics, and by association, the cloud and the distributed architecture that those types of analytics necessitate. All right, so with big data analytics, we will begin where we should probably always begin, which is with the data. The term big data, I think, really started to be used more commonly as organizations begin to amass data from the internet. So I think in the beginning, it wasn't necessarily spatial. It was like weblog files and customer sentiment and internet traffic, social media streams and whatnot. And along with that, another early form of big data was, again, data coming in from sensors and IoT devices. And that also started to really lead into some of the earlier forms of what a lot of people think of when they think of spatial big data. So if data is coming in from a sensor and it's attached to a moving thing, then you accumulate large quantities of movement data. So GPS telemetry is a common one. But this is all kind of in the tabular, like, vector space. And of course, many of us who've worked in GIS for years have been dealing with different things that we might consider big data, like imagery, like terrain, LiDAR, multidimensional data, 3D. These have always been large files, and these data sets are just getting bigger and bigger all the time. There's more companies out there collecting this information on new and dynamic types of assets that can collect information at higher resolution than ever before. This is an example, sort of a very quintessential example of spatial big data. This is New York City taxi data, and this has been used, I think, a lot over the past 10 to 12 years as an example of why spatial, at least vector spatial big data can be very challenging. So I think 1 year of this data is over 100 million records, if I'm not mistaken. And this is like each record has trip pickup and drop off locations, times, passenger counts, fares, things of that nature. And just the trip records themselves make it over 100 million features for a given year of data. And that's not even beginning to get into how big it would be if it was the actual movements of the taxis themselves. And when you take data this big and you try to load it into a GIS client, your experience may not be unlike what you're seeing here, as you just see the data shimmering and constantly loading and lots of points, and you can't necessarily make heads or tails of it. And in some cases, good luck trying to process it. You might try to run a density surface. You might, with this data, want to understand where do trips, begin and end at different times of the day, like what are the spatial patterns of movement. And you can run a process and it might finish, it might not, it might take days. It's very, very unwieldy and hard to work with. And so that kind of gets us back to the classic question of how big does data have to be considered big data? Is 1 million features big data? Show of hands. Is it, how many people would say 10 million records is big data? 50 million? 100 million? I guess I gave it away by saying taxi data is 100 million. So the answer, of course, is that it varies. And the best way I ever heard to describe it was that big data is what you have when your traditional means are failing you. So if you've been to an ESRI presentation on big data before, you've actually probably heard that. I didn't. I stole that from someone shamelessly. All right, so when your traditional means are failing you, what kinds of techniques are applied? So various techniques have evolved over the years. A lot of them have to do with data distribution. So you could take a huge data set like the taxi data, split it out into partitions, and then run parallelized processing on each of those subsets of the data, same process on all of them. And then those different results are assembled back together at the end. And a key aspect of all of this is fault tolerance. So if any particular partition were to fail, like if one of the machines in that cluster were to die, the partition has been backed up, or at least the definition of it has, so that you can rerun just that partition, hold the whole result until you get that answer in there and have accurate results. And the long and the short of what I'm describing here is basically the MapReduce and Apache Hadoop process, or framework and approach, I should say. And over the past decade, Apache Spark has really emerged as the leading framework in the arena of big data analytics. Spark also applies this approach of distributed processing, but it uses, it's kind of focused around the idea of this resilient distributed data set. And one of the key differences between that and the MapReduce approach is that it uses data in memory. And instead of like MapReduce and Hadoop, which do the operations on disk, and it just has a big performance improvement, which is why it's become kind of the leading approach. And at this point, it's much more than a data processing framework. It's a whole collection of, like, it's a library of various things and tools. You can program it in a variety of different languages and so on. And as Spark has grown in popularity, various industry cloud providers have now started providing hosted Spark environments so that organizations don't have to put together their own computing clusters anymore, and they don't have to run that constantly, even if they're not using it. They can just benefit from on-demand compute. And these cloud providers, they're all the usual suspects. You guys know them all well. So AWS has EMR. Elastic MapReduce is what that originally stood for. Microsoft Azure has Synapse, which I think is now folded into Fabric, if I'm not mistaken. And these hosted Spark compute environments are also able to seamlessly talk to these cloud data lakes of data that have started emerging over the years. So if you might have hundreds or thousands of files in Amazon S3, you might be storing your information in Azure Data Lake. And usually organizations are using these when they're collecting data from kind of these new and different sources, and it may not be data that has made its way directly into the GIS. And so because of these trends in these processing frameworks and these cloud providers, it's gotten really important to be able to take spatial analysis and move it to the data and to these architectures where the data lives. So for years, there's been open source spatial frameworks that do this. Apache Sedona is one of them. Some of you may be familiar with Databricks, who are the original creators of the Spark project. They released a library called Mosaic last year, which has vector and raster functions as well. And unsurprisingly, ESRI is moving into this space too. So last year we released ArcGIS GeoAnalytics Engine, which is an extremely comprehensive Pythonic Spark library of spatial tools and spatial functions. And this can be placed directly in any of those cloud Spark platforms that I just mentioned, and you can run these analyses in notebooks against your data that you may have in your data lakes. So GeoAnalytics Engine, if you're familiar with previous incarnations of this particular product, we've had it as a server role within ArcGIS Enterprise for several years. And there's also a tool set in ArcGIS Pro that actually allows you to take advantage of parallelized processing on your local machine. The tools that are part of this engine product are pretty much the same tools that you would find in those other two incarnations. They are tools that allow you to do aggregation of big data so that you can see patterns at, kind of a lower number of summary features. It's tools to do space-time joins. Again, because a lot of big data has a time component, there's lots of spatiotemporal analytics in here. But overall, these are the kinds of tools that, regardless of it being GeoAnalytics Engine, these are the kinds of tools that spatial big data analytics tend to require. Half the battle tends to be taking this huge thing and reducing it down into something that you can work with and running the different summaries that you need so that then you can go to town on your analysis. All right, and so we're going to take a quick look at this in action. The form of data that we're going to use for this example is track data. So in this case, snowplow tracks. One of the reasons that we're going to use this as an example is that a lot of local governments this is the kind of data a lot of local governments are beginning to deal with when they get into big data. And not necessarily snowplows in particular, but public works, vehicle tracks, and similar things. And one of the reasons that they want to look at this kind of information in the case of winter weather operations is because they might want to do after action assessments of the plowing activity so that they can understand coverage, look at fleet efficiency, identify areas where they may want to change the snow route plans and so forth. So this is admittedly a video of the product being used. What we're doing here is we have GeoAnalytics Engine deployed into a Databricks compute environment within Microsoft Azure. And I use the word deployed very generously there. It's basically you copy the library up and you drop it into that environment. There's not really any kind of formal, complicated installation. Let me find my mouse here. All right. So in this case, we're working with a historical data set of GPS points from the city of Chicago. And this data set has only about 1.2 million records in it, actually. And then we also have a street centerline data set for the Chicago area, which is about 56,000 features. So that's a snapshot of the street center lines there. And what we want to do with the data is ask two main questions. The first question is, what road segment was a GPS point on at any given time? And that may sound obvious, but actually GPS data has a lot of drift if you've ever worked with it, or if you've ever kind of seen your point on your phone, you probably know what I'm talking about. And it doesn't always line up cleanly with roads. So first we have to associate each of them with a road. And then the next question is, how often have vehicles made trips across any of these road segments? And this would allow an organization to examine overall coverage, to look at potential needs for road maintenance, and basically be able to understand, if more passes went across a road, then you might need more maintenance later. You might want to, de-emphasize one area so that another can be covered more and so forth. So we're going to see how GeoAnalytics Engine can be used to support this. So the first part of what we're doing next in this notebook, I'm going to show you a lot of Python code in this demo, so bear with me. But the first thing to do pretty much in any analytical process is data engineering and data cleanup. So that's kind of what this first section is. It's basically making sure that each record has a unique ID and a track ID for the vehicle, making sure that the date and time information is consistent, and looking at the coordinate system of the data. And I got ahead of myself, so I'm pausing it briefly there. And now with the data formatted correctly, we're going to go ahead and dive into the questions. So as I said, the first question is about associating every one of those 1.2 million GPS points with a road segment. And to do that, I think I started the video over again. Let me get it back to where we were. So to do that, we basically need to snap a road to a road segment. All right, so in order to snap to a road segment, we need to basically be able to find the nearest segment to any particular GPS point. And we need to be able to do not just that, but understand if it makes sense that the vehicle was on that road at that time. So the snap tracks tool basically does that. This is an example of a subset of data. The original points are in blue, so you can kind of see the drift. And the result from snap tracks are the yellow points. And this basically shows their shift to snap to the nearby road segment. And snap tracks allows us to find a good match, not just based on proximity, but also the logic of the flow of the points themselves. So in this data set, we can also give it some hints in terms of how to do the snapping. I think we used a 20-meter search distance so that we could deal with wide roads, but it's also forming the track as it snaps and looks at the heading and the directionality of the road. So it's using network logic in the process of snapping. So the data table of the results looks like this. Basically, for every GPS point, we know now its street ID that it was on. And we also have the matched geometry or the snapped geometry as well, so that we can create new features based on that if we want to. All right, so the second question is about trying to answer how many times a specific street segment has been visited, or in this case, how often it has been plowed. And we don't want to just count the GPS points, because that's just the number of points on the segment. And we don't want to count the distinct number of vehicles, because the same vehicle may have passed over a segment multiple times, and we want to actually represent that. And so what we can do is create a representation of those journeys, a continuous path of the vehicle over each segment. And the tool that we can use to do that is this tool called Reconstruct Tracks. This lets you connect sequential observations into a line. What you have to use is a unique ID to organize the track, but then it'll sort them automatically by time, and it creates something like what you're seeing here. So this is the continuous path for one particular snowplow, for example. You use a unique ID to group them into tracks, and you can also introduce logic to make sure that you don't create excessively long tracks, even if there's gaps in the data. So for example, we used, I think it's 500 meters and 60 minutes to break up the tracks. So that way, if a vehicle stopped for a long period before it did another pass over its route, we would accurately capture that there were multiple passes there. All right, so when using this tool, we generate a set of continuous tracks for each vehicle. Again, we might have multiple tracks for a vehicle. And then we need to do some follow-up joins. Basically go from the tracks to the GPS points that were part of the track. And from those GPS points, we also have the street ID that each point was on. And so we end up with a table basically that has those associations. I know this is a little bit small here, but for each ID of each GPS point, we have the street ID. That was what we did in the first step. So that's what I'm highlighting there. And then we also have these newly created tracks, and we have a unique ID for each of those. And so at this point, we can really just take this table and count up the distinct track IDs for each segment, which is pretty straightforward, just summary, group by, and so forth. The summary can now be joined back to the street features. We started with just a table here, but we can join it back to the street features themselves that we started with. And then these can be written back to ArcGIS layers for use by stakeholders for planning purposes. So even though we're using Engine within Databricks, within this cloud vendors environment, we can connect back to the GIS. And that could be ArcGIS Online, or it can be ArcGIS Enterprise. And we can write those summary results back to a feature layer. We could also be appending to an existing layer or overwriting a layer. So you could schedule something like this and run it on a regular basis. So here's what that result looks like. These are the streets visualized by, again, the number of times a plow actually went across the street. And this could be used, of course, to review coverage patterns and, make any other changes in plans for the next snow event. Now, I'm sure a lot of you have worked a GIS analysis before where you may have summarized data by polylines or polygons. And the point here is not necessarily that the analysis itself is that different than things you may have done before. In some ways, it is because of this focus on movement data and the ability of these tools to work with movement data in particular ways. But what it's really about is having these spatial analysis tools available directly within these cloud environments and able to work against data that may not be available to the GIS or may just be too big to be used in the GIS. So that was an example with GeoAnalytics Engine in particular. But the two main takeaways I want to leave you with are essentially those two pieces. In most cases, the key things for spatial big data analytics is that they will be tools that will allow you to get insight into spatial and temporal patterns in data. They tend to be really focused for that. And the way they do what they do is all about being able to work with data that's too big for a desktop machine, or even up to massive collections of data. And it's fundamentally all about meeting time constraints. We have a lot of tools that are part of, in our case at ESRI, GeoAnalytics Engine, that also exist in our standard geoprocessing tools, and you may be able to do the work there, but it might take hours or it might take days. And so this is all about bringing those processing times down so that you can get things done faster. All right, so the second trend I wanted to talk about a little bit today is graph analytics. These have been gaining popularity and usage over the past couple of years as well, partly also due to the growth of big data, but in particular connected sorts of big data. So a knowledge graph is a representation of entities that represent things like people or assets or places or organizations. And a relationship would be an association between them. So it could be that this person works for this organization or that an activity occurred. So maybe a person visited an organization or they made a transaction against their bank and so on. And in its most basic form, a knowledge graph is essentially a link chart, as you're seeing here on the right, where the entities are nodes and the relationships are the spokes between them. And in a lot of cases, just getting to a visualization like this tends to be really helpful for certain types of use cases. It tends to help certain types of users really dig in on where to start with a problem. Graph analytics, again, previously probably known as just link analytics, encompass that visualization, but it's usually helpful to think of graph analytics in three main parts. There's the visualization aspect of it, but then there's also graph queries, which allow you to ask an explicit question that uses searching among relationships to get you the answer. So one example of a graph query might be, find me all the suppliers that these two plants both buy from, for example. And then graph algorithms on the right here. Sometimes graph algorithms encompass a graph query, but usually there's a process or a function involved. So it's not just, navigate this graph like 2 or 3 hops out, but an example of a graph algorithm might be, find me the shortest path between these two entities, even if there's multiple paths between them. Things that we're probably used to with network analysis. So the kinds of problems that can be approached with graph, there's a lot of things that can be modeled as graphs, if you think about it, because a lot of the real world works this way. A lot of graph problems are about looking at people networks, so employees and organizations, contact tracing, for example, social media, crime rings. And then there's also transaction networks. So supply chains is a big one, but also maintenance events, financial transactions, orders and payments. And then this is a little bit probably less familiar to this crowd here, but a knowledge network, not to be confused with knowledge graph, is a situation where you might be trying to understand an organization from the outside. So what are the skills and roles that are in this organization and how do they depend on each other? What is the infrastructure that this organization relies upon and things of that nature? So given these types of networks, there's a couple use cases where graph analytics tend to be super useful. The analytics have really exploded in, especially these two at the top. So criminal fraud and threat intelligence are two big ones, admittedly. Fraud is often about tracing activity back through different individuals and shell companies, or, on the cyber side, IP addresses, and are they owned by the same individuals and organizations and so on. And threat intelligence is highly related to the knowledge graph example, knowledge network example that I was just mentioning on this slide. So threat intelligence is often about trying to understand an organization and maybe understand its vulnerabilities. So, order of battle and, where do they have their locations and things of that nature. So very much sort of in more of like the federal government and homeland security spaces. And then coming over here on the right, supply chain management is another typical area, using graphs to represent suppliers and plants and materials, even into logistics and routing. So again, we in GIS think of routing as a network analysis problem in a lot of cases, but graph analytics are also used here. For example, pre-positioning inventory at stores ahead of a disaster that's expected to hit their suppliers. And then some more emerging areas on the left, asset management and real estate management. So one of the questions we get a lot about graph analytics is why. There's probably some problems that I've described so far that you're like, well, yeah, that just sounds like a database query. What's the difference? And really what it comes down to, my understanding at least, is that as these networks have been getting more dense and organizations are trying to put more and more different data sets together and model things in this way, if you're using a relational database, you end up with this really complicated sort of database model with different tables and primary and foreign keys. And it can all be done, but the performance tends to start suffering as data gets bigger and as the networks get more dense. Whereas the graph database technologies that have been emerging have this much flatter performance. And that tends to be what makes the difference, is getting your query answers back in minutes as opposed to getting it back in seconds and being able to move through an investigation much more quickly. So a couple more things here, and then we'll show you guys an example. We've talked a lot about how graph databases model data, entities, and relationships. It's probably pretty clear through some of that graph is all about in its nature, it's all about logical relationships. So there can be organizational hierarchies that you can model in a graph way. You can model dependency maps. One interesting example here is we even have some customers that are starting to use graph analytics to model their GIS infrastructure. So I have a web map and it has these layers, and these layers come from these services, and these are on this server, and the server is over here. Ironically, that is actually how some of our customers are beginning to apply it. Supply chains, as I said, and then also communication networks can be modeled really well with graphs. So, Tim called Amy, who called Suzanne, et cetera. Again, this one does tend to be sort of in the public safety, like crime investigation sort of space. But the reason we're talking about graphs so much today is that what they don't really model that well, of course, is spatial relationships. The spatial relationships between entities sometimes don't exist in any explicit form until you actually see them on a map. Graphs know about logical relationships, they know about stuff that exists in the data, but they don't necessarily know things that you can only discover through, as we all know for years, of GIS. And the first time this was sort of drilled home for me, my first job out of college was for Lockheed Martin up in the DC area. And I was working on a link analysis project at the time, ironically enough. Not what I work on now, but everything comes full circle. And one of my coworkers at the time had worked in this space for many years. And we were working on this project together, and he was telling me a story about an investigation that he'd worked at his previous company where they were trying to find a mole in their organization. They had an employee who was talking to the press and leaking sensitive company information. And they did all kinds of link analysis trying to find the connection between one of their employees and this reporter, and they couldn't find anything. And the only way they figured it out is they put the reporter's address on a map, and they put all of their employees' addresses on a map, and they found out that their backyards matched up to each other. So because their backyards backed up to each other, there wasn't anything in the data that was going to show that. They weren't on the same street. They wouldn't have been able to find it on a street match. Maybe they would have been able to do it based on zip code. I don't know. And it was only these intangible spatial relationships that showed them where to start looking, basically. And so that's proximity, but obviously there's other kinds of spatial relationships that could play a role. So movement patterns, if you actually have movement data, again, this probably shows up more in the public safety, like crime analysis space. But if you get a search warrant and you get cell phone data, then sometimes doing that kind of mining can show associations between people. There's also intersections. So if someone, took the Red Line Metro to Station 5, where else in the, transportation network could they have gone? And then also visibility. So what can be seen from this location? Why might this entity have chosen this spot? Maybe more of a Homeland Security sort of workflow, but hopefully you get the idea. So this trend within spatial data science about graph is really all about just bringing spatial insight to graph problems, basically, and to the graph analysis workflow. And this might start with just visualizing the graph on the map, like in the example I was sharing about that investigation and seeing things that you didn't see before. But once you do that and you form these new connections, you can also persist that data back to the graph, and it can be used by other users as part of a normal investigation. And within ArcGIS, we have a newer product called Knowledge that is getting into this space and working to bring graph and spatial analysis together so that you can kind of move back and forth seamlessly from link charts to the map to discover one thing here and then see how they relate spatially, discover something else when you're looking at the map and then bring it back to the graph and so on. This is right now, primarily, I think the access point into Knowledge is in ArcGIS Pro, but it also has some ArcGIS Enterprise components. All right, so we'll take a quick look at this. This is going to be from the perspective of a supply chain, because that does tend to be such a quintessential example for graph analytics. So in this case, we have an anonymized supply chain network that we received from a customer. And this is obviously a global network. We've modeled it with a knowledge graph. The knowledge graph sits in ArcGIS Enterprise, but we're using and engaging with the information in Pro. And there's different elements in the graph here, from plants to suppliers to raw materials. There's basically several hops of connections between end customers and the overall supply chain. And you can also, of course, visualize the links from the graph in the map as well, assuming the things in the graph have a spatial component, which these do. So we're going to say that one of our suppliers in Texas has notified us that some of the steel parts that are needed didn't pass a quality assurance check. And what we want to know is how this disruption is going to ripple through that supply chain. So what we're going to do is kind of remove the relationships for a minute. In some cases, they can be helpful. I think in this case, they're probably not necessarily getting us to the answer that we want. So we're going to start with just the locations. And then starting with supplier 88, which is the one selected here who has a problem, we're going to expand their relationships to see who they supply, what they produce, and who buys those parts, basically. So that's who supplies them. Here's what they produce. And then the last step here is who buys those parts. So basically there's 3 plants here that would be affected if there's a materials problem from supplier 88. So just going, navigating through the relationships in that way helps us get to that answer. Now let's say that some other information indicates that supplier 226 is suffering from an environmental contaminant. And if that's true, then anything else in that same region could potentially be contaminated. So we can take supplier 226 and we can send them to the map. And in this case, supplier 226 is in Japan. And what we can do is now ask, how would the network be affected more broadly based on the spatial characteristics and not just the graph? So there's some specialized tools now in Pro to help you do some of this stuff. There's this search and filter tool. What we're doing here is executing a graph query against the database that is navigating through from suppliers to materials and manufacturers. And it's also including a spatial analysis question in that query. So imagine, if you will, that you were running a geoprocessing tool at the same time as doing this query, basically. And it runs the query back on the server, which is where the graph is, because the graph is hosted in ArcGIS Enterprise. And so we can get the results back and we can visualize them as a new link chart. And I'm going to pause the video for a second just to make sure to call out what we're doing here. So on the right-hand side, what I'm circling, this is the first link chart that we expanded manually when we started with the supplier that had a problem. And we said, okay, who's directly affected since we know this supplier has a problem? And we got back 3 plants as the answer of who would be affected downstream. But everything on the left is what we found out by using spatial location as part of it, by saying, okay, if upstream there was this supplier that had a regional contamination, who else in that region might be affected? And now basically we can find 9 more plants that are downstream from those suppliers that may also be affected and disrupt the supply chain. So that's kind of, it's a very sort of simple, at least reasonably simple example of how, again, it kind of comes back to we have this tagline at ESRI about see what others can't. And this is kind of literally that, right? Like there was no relationship from the contamination perspective in the graph database, but using spatial proximity is what allows us to look a little bit more broadly. So there's some other ways, I'm going to pause it again real quick here. There's some other ways we can look at our data with ArcGIS Knowledge. What I have up here on the side is, again, the search and filter pane, and it allows you to kind of run different metrics so that you could see things in different ways. So for example, if we want to know what part is affected the most, we can look at who's the most connected. And we're hovering over part 100 here. We can see that that part is the most connected. And so if we had an issue with that part, we know that there would be shortages of that in the future, and that might be a problem. And then there's also some other metrics that you can use. We're not going to get too much into this today because you could probably do multiple sessions on ArcGIS Knowledge, and in our user conferences we do. But there's also centrality metrics that you can use to understand different things about your network. So if you want to see who do we depend on the most from a supplier perspective, you can sort by some of these centrality metrics. And in this case, we can say, okay, supplier 10 is who we depend upon the most. So just a few quick examples, kind of talking about how ArcGIS Knowledge and more generally graph analytics and the integration of spatial analysis can really sort of allow you to see problems and explore situations and ask questions in new ways. It's not to say that you couldn't necessarily answer these questions by running a geoprocessing model. But if you did that, you would have to go collect all the data sets, and you would have to figure out how to join them all and build out your geoprocessing model. And you'd have to do those joins and that analysis every time you have a new question. And the idea with graph and spatial analysis is that the data is modeled as relationships at the beginning, and then you can just mine and explore in a more intuitive way. So hopefully that begins to give you a little bit of an idea of how that works and how you guys might apply it. And so the last trend we're going to talk about today is GeoAI and how AI in general is being used in geospatial analysis and how it's getting incorporated into ArcGIS. So we've been talking about what we call GeoAI at ESRI for a couple years. But I think in the past year, ever since the release of ChatGPT, the version that was released, I think late last fall, I'm blanking on what version it was, AI has almost become a household name at this point. It feels like every organization is trying to think about how they can apply it or how it's going to disrupt what they do and how to use it with care. At least we hope most organizations are, right? And AI, of course, refers to these newer algorithms and techniques that essentially can perform work that humans previously would have had to do. It's described as techniques that can see, that can learn, that can create, and it's mimicking human intelligence more closely than ever before. And spatial analysis, of course, is being able to take spatial data and generate useful insight and information that can drive decision making. And as we said earlier, we really see, at ESRI at least, we see geography and spatial analysis as being able to model the real world in really exciting and comprehensive ways, being able to take disparate information and put it together and craft an accurate view of the real world around us. And so in many ways, we think of GeoAI as the intersection of where artificial intelligence and spatial analysis meet. It's the intersection of these two things. And that's really powerful because the only way that AI gives good results is if we give it good information. That particular point, depending on who you talk to, people might debate that. They might say, well, AI can learn, it can build better things than what you give it, which may be true. But at base, if what you give it isn't an accurate view of the world, the potential is there for AI to produce something that's less than accurate, and we can make, really dangerous decisions based on that. So what we look at with GeoAI is using spatial technology to create the best models possible and being able to, for lack of a better word, help AI make decisions that are going to reflect a correct view of the world, if you will. And what we're seeing is people using GUAI in two main areas. One is to generate rich spatial data. We're going to talk about that in just a second. And the second is solving complex spatial problems. So we'll take these one by one. The generation of spatial data through AI is really the most common way we're seeing people use AI in GIS. And so this is the class of problems that on some level in the past, typically people have had to do manually, if you will. So this is digitizing features off of imagery or counting buildings, or just in general interpreting imagery and coming to conclusions. But obviously, as we discussed in the beginning, in the big data analytics part of it, this data is not getting any smaller. These rasters are bigger than ever before. There's more and more imagery being collected, and it's just not feasible anymore for us as GIS practitioners to have to do all this manually. And these deep learning algorithms are getting extremely good at doing this as well. They're extremely accurate, and they're able to help us operationally scale this work more so than ever before. And this is going to be completely transformative to be able to bring in all this data and turn it into information immediately. It's going to completely empower the next generation of spatial data scientists. So on the one hand, it's really, really exciting to see. And this side of GUAI is also the side that it's actually pretty possible to get started easily. For example, within the Living Atlas in ArcGIS, we have today over 40 pre-trained models that you can use to get going with your own information and to solve or to generate your own data, I guess I should say. These are things like classifying, point cloud classification, object tracking, like against video, image feature extraction and detection. And you're not limited to just what's in the Living Atlas. You can take these and you can adapt them and you can refine them to apply to your data and to your study areas. All right, so we'll take a quick look at a few demos of generating spatial data using GUAI. First, we're going to take a look at generating data from imagery and then also from point clouds. So this first one is about the rapid identification of building damage after a natural disaster. In this case, this is after the Woolsey fire, which was a wildfire that burned in Los Angeles and Ventura counties in late 2018. And in this case, ESRI was collaborating with USAA Insurance, actually, and they wanted to identify building footprints in the area and classify them as damaged or undamaged so that they could actually submit claims for people right away and start get that process started and get them the help that they needed before they even had to kind of submit it and do it. So there were about 10,000 building footprints that were in the perimeter of the fire. And the first step is basically to collect training samples. And there's some new built-in tools in Pro that are set up specifically to do that. So that's kind of what we've opened up here. And this part of it does look like, the classic way of doing things, right? Like you're going in and you're digitizing a feature, but you're basically saying, okay, here, this is a destroyed building. I'm going to go ahead and define the class of this and set the color for it in terms of how you want to visualize it in your map session. And we repeated this process and captured a bunch more training samples in this way. There's about 10,000 buildings to classify. I think in this case, we created training data for about 900 buildings. So we're about to turn the buildings to classify are in the green here, and the ones that we trained it on are in the red down here in green. And then there's basically a 3-step tool process in Pro to kind of run this on the rest of the area. So the first step is to basically export the training data. That creates a bunch of image chips that can be used to create the deep learning model. And then the next step is to take those chips and send them into the training process. And that usually is the longest part of all of this, is training models. And then the third step, once you output a model from that tool, you can then take that model and then you can run it on much larger, broader study areas, which is what we did in this case. And so the output is this. We classified about 10,000 buildings, I think, in about half an hour in ArcGIS Pro. And if we zoom in here and take a look at some of it in detail, my colleague who worked on this project said that, he thinks this is even better than what a trained assessor can do. And them might be fighting words, but it is, as you can see, pretty accurate and pretty impressive. And that's in half an hour, basically. Well, I guess if I'm being honest, there's obviously the process of capturing the training samples themselves. And my colleagues didn't quote how long that process took. But actually running the deep learning model was about half an hour for all of that. And given that you're doing this in ArcGIS Pro and you have access to all of the other geoprocessing tools in Pro, you could immediately go on to do additional forms of analysis. So one of the things they did just to kind of show USAA some options at the time was to feed in the damaged buildings into, let me pause it here, network analysis tools, specifically, I think, location allocation. So they basically looked up the nearest shelters within 20-minute walk time of each of the damaged buildings, just kind of as an example of, if the insurance company wanted to provide that information proactively to members who they deemed were affected, which is pretty interesting and cool. All right, so that was an example using imagery. This next brief one is going to be using point cloud data. And what we're wanting to do here is find where trees and vegetation are infringing upon utility lines. And the goal, of course, is to proactively find areas so that we don't have damage and spend excess money and have customers without power, obviously. This data might look classified already, but it's actually just classified by height. And again, using the pre-trained models in the Living Atlas, we were able to run that on this data and extract and separate the point cloud into buildings, into vegetation, and into points that we classified to belong to the utility lines themselves. And then basically we can just use 3D intersection tools to automatically find the locations where the vegetation is infringing on the power lines. And I think we move around here in a couple places and kind of look at that. So these are just two examples of things that you can do with the deep learning pre-trained models on imagery and with the point cloud data. But you can also use some of the pre-trained models to help you work with video, to work with time series data, and even to work with unstructured text and extract spatial data from text. What's interesting about these in some ways is that, of course, we're not necessarily generating the data simply for the fun of it. The point of doing this is because you have important downstream processes and analyses that you need to use that information in. And that's kind of what the second half of GeoAI is actually all about, is solving complex spatial problems. And this is an area where the tools that are available to you are things that, on the one hand, are using statistical and machine learning capabilities. And they might be using non-spatial methods, but on spatial data. So an example of that is random forest, for example, which is really good at predicting for a number of spatial problems. And then there's also spatially explicit statistical and machine learning tools where they use the geography or their location, often in the form of doing neighborhood analysis. And that actually is brought to bear on the prediction. Other capabilities in here that leverage AI in various ways are things that might be finding clusters or finding patterns. The output of those tools is not necessarily to predict something. The prediction, if you will, is that we think this is a cluster, that we think this is a pattern. But these are important steps typically in generating hypotheses and figuring out what questions you want to ask. All right, so our last working example today is the second half of GeoAI here, and we're going to look at predicting housing value prices, and we're going to do this in two different ways. On the one hand, with a non-spatial method, and then with a spatial method. So this is housing prices in Seattle, as you can probably tell from the geography. What we want to do is take this data and model it and see if we can make predictions about housing prices from this. And we're going to do this in two different ways because with this half of GeoAI, if you will, one of the things that's really important to do is to try different modeling and prediction approaches and seeing like what makes sense for your use case and for your problem. And that's what we're going to do here. So the housing data here that we're looking at, it's already symbolized by value. So houses that are more expensive, unsurprisingly, are in green. Houses that are less expensive are in red. And If we look at some of the different attributes of the data, we're going to zoom in here. We can see that the data has things like bedrooms. And one of the things you can also do as you're working with data and you're figuring out how to model things is you can use these charting capabilities in ArcGIS Pro to look at how attributes and what you're trying to predict relate to each other. So this particular chart that we're pulling up here, this is square footage and housing value. It probably doesn't surprise anyone that square footage relates to housing value. Now, the first way we're going to build a model around this is with new tools that are also part of this GeoAI tool set that we have in ArcGIS Pro. And this tool that we're going to use is called AutoML, which unsurprisingly stands for Automated Machine Learning. And what it does, it takes a more recent approach where it trains and compares many different machine learning models automatically. It tweaks parameters, and it automatically selects the best performing model for the inputs that you give it. And this can be a useful thing to experiment with because it can help you learn about your data as well. So you might spend less time running something like this than trying all these different models yourself. So what we're showing here is that the input to this, I'm just going to pause it for a second. The input to the AutoML tool is obviously the data set, the thing that you're trying to predict, which is price, which has the checkbox there. And then you can choose the variables that you want to use to make that prediction. So in this case, we've selected bedrooms, we've selected bathrooms, we've selected number of floors and waterfront. We're tinkering with a few different variables here. And you can also choose which algorithms to test. If you kind of know that you have one that you think is going to be better. If you don't, you can just say test them all, which is actually what we're doing here. And the output of this tool is not actually a map, it's reports. So bear with me while we talk through these reports. These are all the different models that were evaluated. It shows you which is the best performing one. And we're going to shortcut this a little bit and just kind of point out that the best performing model that we found with this AutoML tool had an R-squared value of, I think it's 0.88. Kind of hard to read, I apologize. But the R-squared value is 0.88, which means that the model that was selected as the best explained 88% of the variance in the data, which is it's pretty good R-squared value, all things considered. We, as data scientists, we might be happy with that and said, okay, we've got a great model. We could use this perhaps. But we're going to try something else here. So I'm going to step back to the map for a second, and we're going to just, again, look at the data. And we can really, I mean, I do, I hope that you guys do as well as GIS practitioners, really see that there are some spatial patterns in this data, obviously. It's not that, you know, high values are completely intermixed with low values and that there's no spatial pattern to it. There's clearly some areas where housing values that are higher are clustered or grouped together, and some areas that more commonly have lower housing values. It's probably not a surprise to anybody that housing values are somewhat affected by your neighbors and that location matters, right? So in this case, we can use another tool called geographically weighted regression. And this is a essentially linear regression, but it performs hyperlocal regressions across every value in the data set. And it basically uses the values around a location in its neighborhood as part of the predictive process. And so with this tool, we're only going to select one variable to predict on, which is square footage. And besides that, we're just using that variable and the locality and the values of the houses around any given house in the prediction. So we'll go ahead and run this, and you're going to see some, it's like I mentioned, you're going to see something, and then it goes away. All right, let me pause this. The report from the geographically weighted regression is what we're looking at here. And I only have this up for a second in this video, so I'll just clarify what we're looking at here, which is one of the values returned with this report is that the R-squared in this case was 0.89. And so it also did a really, really good job of explaining the housing value data. And in this case, it was a model that was only using one variable to predict, which was the square footage itself. And so I think it just kind of shows the power of spatial patterns in terms of predictiveness, things that can be intangible with regard to spatial proximity, kind of like what we were talking about with the graph analytics. And the fact that this model is simpler might be useful depending on the problem that you're trying to solve, the way you have to do the predictions later, the kind of data that you might have later. So it's not that one method is better than the other. They actually had very similar sort of metrics on that aspect, but the simplicity of the model with the spatially explicit algorithm is what we thought was kind of interesting here. All right, so just a little bit to give you a sense of some of the predictive capabilities available, as well as how powerful the spatially explicit capabilities can be. The last thing that we're going to just say here with regard to AI to leave you with is that, obviously at ESRI, we realize that AI is incredibly revolutionary, and there's a lot of really exciting things our customers are doing with it. We're really, really impressed at some of the strides that our customers have been making. But we do want to recognize that there's a lot of discussion about AI and how to apply it with care. And we're really, really considering every aspect of that as we build AI capabilities into the software. One of our perspectives at ESRI is that with AI or with statistics or with anything else, if we stay really, really focused on the problems that we're trying to solve and not necessarily get, caught up in the latest tool or the latest algorithm and whatnot, then it can be really a lot easier to make sure that we're doing responsible work. And so as we build AI tools into the software, we're paying attention to what kinds of use cases is something, really good for, putting that in the documentation, being extremely transparent about what's going on so that you have as much information as you need to adjust the different parameters. And if anything, a lot of these tools have a lot of bells and whistles because we want to enable you to apply them in ways that make sense for your problems. So hopefully going forward within ArcGIS software, GUAI is not going to be this new hammer that you're going to take out and apply to like everything, but it can be another tool in the tool belt. And hopefully in some cases it might make sense to use it. In some cases it might make sense to use it in conjunction with something else. And we're just going down this path very, very carefully. All right, so to wrap up here today, I hope that some of this gave you guys some ideas for new tools and capabilities that might be applicable to what you're doing. I touched on 3 things in particular within ArcGIS, Geoanalytics Engine, knowledge, and some of our GUAI capabilities. But I do want to make sure that we cover the fact that ArcGIS is a really comprehensive system for spatial analytics and data science in general. We know that there's a lot of different problems our users are trying to solve. There's hundreds of different data formats that people need to bring in, and we have tools and capabilities for working with that data, even if it's, I just need to run a summary analysis and understand where my patterns are, all the way to some of the more complex things we talked about today with making predictions. And the other thing to keep in mind is that these capabilities they're all pretty much available in Pro, in our main desktop application, but there's also a number of other experiences now for these analytics for different types of users and knowledge workers. So you don't necessarily have to be a full-blown GIS professional to be able to take advantage of some of this. Obviously today we showed Geoanalytics Engine, which is, it's not that it's not a professional that needs to use that from the notebook and scripting perspective, but it is something that makes spatial analysis available to somebody who may be more of a general data scientist instead of a GIS user. And then there's tools like Insights, which allow you to explore information in really dynamic ways with lots of different views. So there's a lot here, but it's all about meeting you where you are in your spatial analytics journey, and hopefully equipping you with the right access points into the technology to help solve your problems. And so with that, thank you. Sorry about all the computer issues. We fortunately got it back every single time, so hopefully that just kept you awake after the lunch break. And this is your ESRI team that's here this week to support you. A couple of us are doing workshops, so you've seen us there already, or you'll see us there tomorrow, and we look forward to engaging with you. Obviously, we have a booth. You can't find it, but no, I'm just kidding. We do have a booth, and so several of us will be there and looking forward to talking with you guys, whether it's about analytics and data science or whether it's about anything else you're working on. So thank you for your time. Appreciate it.